Right, good morning. Welcome to Crawley, sunny Crawley. Today we're going to be talking about bone, but it's a lot more than just a skeleton. So we're not going to be just talking about bone, but all the ramifications involved with bone. Now, one of the things we're taught in the update in September was associated with when people get their symptoms and how to diagnose this. So I put a couple of examples here of pain, and we all treat people with pain, and the question is, why does pain sometimes get worse at certain times of the day or night? And why sometimes does it almost disappear and sometimes it comes on intensely? So here's an example of someone who gets backache in the afternoons. And you may say, well, this is usually associated with something they probably had at lunchtime, which may be true. So it could be something that they've eaten or drunk at lunchtime that is creating an inflammatory response, such as an allergy or a chemical toxin. That could be one reason. Or we can think about our meridians and say that it could be around the bladder time, maybe small intestine time, but bladder time, and possibly early into the kidney time. This is one of the most common symptoms that we get is, why do I wake up during the night? And by the end of the morning, you're going to be able to tell the people who do wake up in the middle of the night. And that's much more exciting, because you can say, oh, do you wake up between 3 and 5 or between 1 and 3? And they say, well, how do you know? It's a dreadful time. You know, I'm always awake then, and I can't get back to sleep until 5 o'clock. And then I go back to sleep, and the alarm goes off at 6, and then I feel shattered and so on. So one of the questions that we always do with case history is ask how people sleep. And sometimes they say, oh, not very good. So do they have difficulty in starting to go to sleep? Do they sleep lightly, or do they wake up at specific times? So these are questions which actually have a really good, important meaning. And we'll be able to diagnose what it is that wakes this poor girl up at 4 o'clock. So we're going to start with what we did at the update and update that again. And this is something which I learnt from a friend of mine, Tatiana Chernysova, from Vladivostok in Russia. And she presented this as a paper at the ICAK 50th anniversary in Washington in the summer. And Jill and I listened to this, and it was done through translations from Russian to English. And it was very impressive, but at the same time very mystifying. And it was about radiation and bone density. And I thought my conclusion at the end was that radiation was probably the cause of bone density problems of osteoporosis. But she gave me a book, and this book happened to fall out of my bag when I was on holiday, and I thought, oh, well, I'll read this. And everybody else takes a novel, but I take a book on radiation. I did have another book as well, but this one, and I thought, somebody's trying to tell me I should read this. I read this. It's about 48 pages, and you can download this book yourself online, this booklet, and it's very, very interesting. And it really rang true to me that what these couple of people were saying had an element or a strong likelihood that what they said was actually true. And in fact, the radiation was a good thing and emanated from the human body and was involved with bone density. But I thought it was a damage that the people accumulated radioactive isotopes in the bone, and that's what caused the problem. But in fact, it's a loss of the radioactive isotopes in the bone which lead towards ultimately decalcification, etc. So it's going to give you a different idea about the bone density altogether. So I'm going to just introduce this first of all, and then you'll see where we'll be coming from for the rest of the day. So I think it's important to understand a couple of terminologies first of all, or I need to understand a couple of terminologies. The first one is what radiation is, and here we're talking about gamma radiation, and we measure gamma radiation in sievert or SV units, which is a standard international unit of equivalent dose for which a gamma ray is numerically equal to a gray, and the gray, which has units of kilojoules, joules per kilogram, is the international unit of absorbed dose and is the amount of radiation required to deposit 1 joule of energy in a kilogram of any kind of matter. What that really means is they can measure radiation and whether it increases or decreases, and that's all we need to know. Gamma radiation itself refers to an electromagnetic radiation of an extremely high frequency and are therefore high energy photons or particles or waves of light. They are classically produced by the decay of atomic nuclei, so you're all familiar with radioactive materials above 81 in the periodic table, which gradually decay as they transition from one high energy state to a lower state, known as gamma decay, but may also be produced by other processes, in other words, from cosmic radiation and starbursts and things. So between, now quoting Tatiana and the Russian booklet, between 2005 and 2011, American and Russian nuclear scientists measured an annual cycle of the maximum radioactivity count in January and February, with the minimum in July and August for 7 years in a row. This experiment has only been performed 3 times from the moment of the discovery of radiation in 1896. So we're all probably familiar that radiation is random. All experiments, you can't predict when radiation is going to occur. Now, I woke up in the hotel here last night and there was a noise, a click, almost like someone knocking on the door, but 2 doors down the passageway. So it was like a little bell ringing. And it was just loud enough to sort of wake me up, but not too loud to think it's my door or our door. And it was really annoying because it was at random. Okay, it would do it, 10 seconds later, the same thing, and then half an hour later, it would just go beep, beep, and then nothing for half an hour. And this is what radiation is like. So in the morning, I thought it was someone pressing the lift shaft because we were quite close to the lift. There was an ice-making machine by the side, and I thought it was when it switched on and off. But in fact, it was the air conditioning in the room. So as the temperature rose or decreased, it switched the thermostat, and it made this little noise, and it was really annoying. But it was at random, of course, as the temperature changed from up to down. And that's what radiation is like. And that's what we've always assumed radiation to be like. But the Russians and Americans, and this has only been done 3 times for a 7-year period, noticed that the cycle, the annual cycle of radiation output from the ground, changed between the summer and the winter. And in the January and February, it was maximum, and in August and July, it was lowest. Okay? So there were changes in an annual cycle. So this is the first thing that we want to understand, because we'll see that radiation occurs not at random, but is predictable in certain circumstances. And the first one is that it changes on an annual basis. A conclusion was made based on the statistics that changing of the radioactivity was related not just to the Earth's rotation around its own axis, which would be a 24-hour cycle, but to the changing orientations of our objects in relationship to the Sun. The Earth moves around the Sun, as we know, in an elliptic orbit, not a round orbit, but more elliptical, at an average distance of 150 million kilometers from the Sun, with the average speed, this is the Earth moving around the Sun, at 29,765 kilometers a second. That's fast, isn't it? It's a wonder we all stay on. So you have to hold on, But luckily, a thing called gravity actually holds us down. If there was no such thing as gravity, we'd be way up. So that's some speed. The speed is not constant, however. In July, when passing the aphelion point, it is minimum, whereas in January, when passing the perihelion point, it is maximum. So what is the perihelion and the aphelion point? Here we are. This is the distance of the Earth from the Sun. So the perihelion is the maximum speed, is when the orbit is, this part is closest to the Sun. And this is at the 4th of January in 2014. Obviously, there's a slight variance year by year. Okay, and the aphelion is the furthest distance, and the minimum speed, or the slower speed, is on the 4th of July 2014. So we just passed that. Okay? So this is the distance. And this affects the radiation outputs in the Earth. So here we get more output. So we get buzz, 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 buzz. Okay? And here we get buzz, buzz, buzz. So much slower at this point. So the distance from the Sun. So the Sun has an influence on the Earth. Okay? Surprise, surprise. Okay, radioactivity appears to depend on the Earth movement speed. In July, the radioactive... we said that. Okay. Late in the 1990s, investigators commenced in Russia regarding low-energy nuclear reactions which occur in the human body. They noticed with very sensitive equipment that there was background radiation that we're all familiar with. Even in this room, there will be background radiation. Okay, you can't escape from radiation a certain manner because it's in the elements, it's in the ground, it's coming in through the air and so on. But they noticed with sensitive equipment that there was a radiation even a little distance away from a human body, which was coming from the human body, which was greater than the background radiation. But it was measurable with sensitive equipment. All the investigations were performed by nuclear spectrometry and radiometric survey methods, so very, very sensitive equipment. Investigators using a product, and this is a Russian product which I'm going to talk about, called Stardust, and it's called Stardust for a particular reason, because there's something magical about it, but also everything ultimately comes from the stars. So everything that we see here is just a composition of 100 or so elements, and it's exactly the same elements which are in the stars, which are in the moon, which are in the faraway away galaxies at all. So everything ultimately came from a star and the explosion of stars. And its effect, the stardust, and its effect on the gamma radiation indicated counteracting carcinogenic factors in the body, slowing down of malignant neoplasms, expressed gerioprotective, that's older aging protective side effects, reduction of average body temperature and levelling of hormone profiles, average and maximum life expectancy increase in humans and in animals. So this stuff was pretty magical, or is pretty magical. So it offers a lot of protection and regeneration possibilities to humans and animals. The investigations did not reveal any active components in the preparation. So this made it not a medicinal compound, but more as like a nutritional food supplement, if you like, that there was no active ingredient in there that they could actually measure and say this had a biochemical effect. There was no explanation of the mechanism of the influence on body physiology of this stardust. With the first measurements where radioactivity indicators were used, it was noticed that when the preparation was administered, the indicators located 5 to 10 centimeters away from the human body recorded increased gamma radiation. The energy emission was extremely low. The stardust itself contained no radioactive elements. Okay, so we're not actually putting a radioactive stardust into the human body and then measuring the increase. The stardust has no radiation coming from it, but when people took the stardust, the radiation field from the human being increased. Right? The preparation had no chemical elements or radionuclides, in other words, those that break down and give radiation, that could influence energy changes in a human in the gamma quantum spectrum. The preparation demonstrated its activity only upon interaction with the internal medium of the human body. Researchers face the issues as to whether human radioactivity is an incidental phenomenon in a human life or not, and whether a person interacts with his surrounding world by means of his own radioactivity or not. So they didn't really know whether radioactivity was normal from a human being or abnormal. It is known that a human cannot influence radioactivity or radioactive disintegration in natural conditions. So in other words, we don't have no effect, no direct effect on when that radioactive material decides to decay and give out a gamma radiation. We can't influence that at all. The increase in human radioactivity was extremely low within the range of the natural radiation background of 0.09 SV units to 0.24. The observation showed that the short-term increase in human radioactivity is safe for his health and life. So in other words, the person didn't suffer from radiation poisoning. You know, on my first trips to Russia with Dr. Schaefer, Joe Schaefer and myself in 1991, we came back with a good dose of radiation. So both of us, Joe and I, know what radiation is like. And you feel extremely tired and to a very abnormal degree. And this is not this. This actually enhances life and function. When a human becomes a source of radiation or electromagnetic emission, the assumption was that a fetus, this is the unborn baby, becomes a source of electromagnetic radiation in a certain period of existence. So if a human being emits radiation, what happens to the fetus inside? Does that fetus obtain radiation and emit radiation from the moment of conception, or sometime during the development, or at birth or afterwards? And that was the question. Observations were made between 12 weeks and 39 weeks, in other words, between the first signs of pregnancy that they could detect and measure to the time of birth. A pregnant woman, even at a later gestational stage, that's in the last couple of months, was found to have no difference from a non-pregnant woman of the same age and weight in a control group. So a pregnant woman has exactly the same radiation output, gamma radiation, as any other woman, or any other man as well, right? So there was no difference. She didn't have an increase in radiation because she was carrying a child in addition. So there was no difference at that point. Further, in the delivery room, taking 5 spectrogram readings, the mother before delivery, so the mother's there before delivery, the measurement on the mother after delivery. So she's had her baby, see whether there's difference. The child at its first breath. The child at early postnatal supervision. Okay, so at that point it's on its own, it's had the cord cut, it's on its own, that's early postnatal supervision. And then the child at a later postnatal supervision, it's anything from 10 minutes to a couple of hours later. Right, those were when all the readings were done. And what we can see here is the diagram events that count rate of the gamma pulses. The vertical axis shows the gamma pulses per second on here. Now, what we have is the green is the background radiation from the room. That, you see, is constant right the way through. And then we have the mother here. What we see during the pregnancy is going straight through here. And then we have the child, which is in the red. So the red we see here, no difference really on the baselines until the first breath. The first breath, something happens to the child. The child becomes a nuclear reactor. Bang! And within 10 minutes or so, that's then calmed back down and comes in then the same as an adult. So more or less, they get this huge burst of energy, and then it tails back down to what they're going to have probably for the rest of their life. But something magical happens at this point to the child. So here we see again the mother's radiation, the child's at the moment of birth there, and what happens afterwards. And the green is the background. You see the background radiation hasn't changed at all. But something's happened to the human body, to the mother and the child at the moment of the first breath. The assumption that energy redistribution occurs at the moment of delivery was not proved. Okay, so this is the point, that it's not at the moment of birth. Analysis of the spectrograms per delivery allowed for a conclusion that there was no energy redistribution or energy transfer from the mother to the child. So in other words, the child didn't get this burst of energy from the mother. The mother's didn't change at all. She didn't give the energy she gave all her blood and her nutrients and things, but this energy, this gamma radiation that the child emitted at the first breath, didn't come from the mother. Okay? So the question is, where does it come from? Okay? As of the moment of the first breath of the child, and that's different from the actual birth, okay? So the first breath recorded and measured activity of radionuclides is observed, which do not show during the mother's contractions. So even during the contractions, there's still no radioactive output. Analysis concludes that energy is transferred to the child with the help of a nuclear reaction. In other words, there's a transmission of nuclear energy, radiation, in other words, to the child. This is a single and simultaneous exposure throughout the energy spectrum. And here we see the fact of measured activity of the nucleotides was detected. Now, what Tatiana's put in is the different ones like plutonium, sodium, etc., beryllium, which were not noticed during the mother's contractions. Newborns who were not viable, in other words, they didn't show this radiation, tended to die in the first hours after birth, and especially of respiratory failure. So this is a vital part of the health of the child on its way. And something happens for a particular reason, as we'll see. So we know that everything above here is radioactive. Above 82 here, we get into the radiation. So all these higher, heavier elements are present in the tissues in the body. We know that, okay? We're actually made of far more than the 34 elements which we're generally based on in analysis, okay? We have found, or they found, as we'll see later, 64 elements in human teeth, okay? Now, some of them may not be essential, but they're still there because we're actually made from the earth. And so even these higher ones are there in very, very small amounts. So we actually have radiation from the elements. But something makes these elements start to decay at particular times in our life. And my main one is when we take our first breath. Okay? So we are a small radioactive unit for a particular reason. The spectrogram, that's how we measured it, of a child at the first breath differs from the mother's spectrogram with a lesser number of events in the later postnatal supervision only. An hour later, a child's spectrogram is similar to the spectrogram of an adult. This is up to now has been an unexplained phenomenon. So an hour after the child is born, it's emitting radiation to the same level as the mother and everybody else. Okay? So this is really quite incredible, isn't it? That something happens at this first stage, which is life itself, actually you can measure. Failure to measure this nucleotide activity in a newly born child indicates a poor prognosis. In the period of silence after the birth, and those of you who've been in the delivery room, fathers and mothers, when the baby is born, there's that moment of waiting, isn't there? And what are you actually waiting for? The cry, yes. But you're waiting for the first breath, which is usually associated with a cry, and because the lungs are not inflated until the moment after birth. Okay, the lungs are right up here, aren't they? And when the baby takes that first breath in, it's like blowing a balloon up. Okay, and of course they're full of mucus and all sorts of things, and that's why they tend to cry. Now, there's a very important phenomenon occurs at this stage. Okay, and this is the key to the understanding the whole lot. And we are as guilty as anything in this country and most of the Western world, is as soon as the baby is born, the midwife comes in and cuts the cord. Okay? The baby hasn't taken its first breath. Okay? That baby is relying upon the blood and the oxygen from the mother, okay, until it takes its first breath. Okay? When it takes its first breath is when you should cut the cord, okay, because then you're on your own. Okay? So you're on your own, kid, from the moment your cord is cut. Okay? So if you cut that cord prematurely and the child hasn't taken the first breath, they're not going to produce this reaction. Okay? And you'll see why they have this radioactive burst at the moment of the first breath is for one particular very, very important reason. Okay, so failure to register this will lead to a poor prognosis as far as the health. Even elements like uranium, and transuranium mean the elements either side, which are highly radioactive, of uranium are not registered. If they're not registered, there is a development of respiratory standstill after the first breath and intensive care is required. So you wouldn't believe that we actually contain uranium, plutonium, etc. in there, and these things become alive. But every element in the universe potentially has radioactive isotopes in very small amounts. So even carbon has carbon-12, carbon-13, carbon-14. Oxygen, water, oxygen, hydrogen as gases have heavy water as they're known, heavy hydrogens. Okay, so if we fail to register this radioactive output, then the prognosis is poor. An unknown source of energy transfers energy to a newborn human with the help of a highly organized energy medium. They don't know what to call this. There's no sort of word. So if you have a sudden burst of energy, okay, in this case radioactive or gamma radiation, which is just a source of energy, it has to come from somewhere. So if I have given you, I'm the mother of you, or the creator if you like, and I give you the energy from me to you, it has to go through a medium in between. It can't just go from me to you, okay? It has to travel, okay? And that travel means it has to go through a medium. And what it is, it's radiation. And radiation, as we know, are particles or waves, photons, which when they're observed in quantum mechanics, they act more like particles, and when they're not observed, they act more like waves and can pass through any material, including the human body. So you can't protect from gamma radiation unless you have a real thick lead line around you or a big concrete wall. But generally, radiation of a gamma radiation will pass through. Milder radiations like alpha and beta can be blocked from distance and from even pieces of paper as far as alpha radiation, but beta is a little bit more dense. But gamma will pass through thin sheets of even of lead. So this energy has to go into the child, and the question is, where does it come from? The same phenomenon occurs with all animals, and so they studied mice and rats and other animals, and they found that they were all the same, that there was a radioactive output at the moment of the first breath. It is thus friendly. This is what the Russians like to use these words. Are people friendly, or is this source of energy friendly towards us? And obviously it is, because it gives its life energy to all forms of life. If we consider that every living human has a part of this energy, which is the source of the energy is given it to you, away by the uninvestigated phenomena, the power of such a phenomena is enormous and may well lie outside the boundaries of laws known to mankind. A body that emits light or heat loses energy. Okay, so if I give you energy, then I'm going to lose my energy to give to you. So the source has to lose a little bit of energy in order to give it to you. This energy is not manifest as energy of any other body until radiation reaches such a body. In other words, it transfers the energy through radiation. Therefore, if the sum total of all energies in a system must stay constant, that emitted energy must exist as radiation energy in the interim period. After a human enters life, that's when your cord is cut and you're on your own, kid, energy emission and redistribution occurs in his body every day. Now, this is the next... So we've seen that radiation varies from summer to winter. Okay? So that was the first phenomenon we have. The second is we have a burst of radiation from the human body. The human body has a radiation, and we have a burst at the moment of the first breath. Okay, so now we've met three things which you haven't known before. Okay, hopefully. There's a lot more to come. Okay? So after a human enters life, okay, that's when you've had your cord cut, energy emission and redistribution occurs in his body every day. So every day we emit radiation. But as recorded by nuclear spectrometry and radiometric methods, energy emission occurs principally 5 times a day. So this emission is not constant. Okay? It goes in waves. And this is the waves. Now you should have has everybody got one of these? Okay, could you make sure that everybody has one of these? This is, I decided, because so many things are on the chart and then I move on, talk about other things, people like to stay on some of the diagrams. So what we're going to do is we're going to give you for each table to use at this stage, a laminate, okay? And then you'll see the chart here, because this is really quite significant. So the chart at the top there shows the background radiation. So the red is the background radiation, okay, in this room. And then you measure what the time is, and the time is at the moment 10:30. So you find 10:30 here, and you'll see that the radiation is at a low level. So we're not really doing very much as far as our radiation at the moment. But a little later on, at 11:30 to 12, we get a big boost. So stand back. It's not just the coffee at break time. Okay? There is a big boost coming your way. Okay? And the question is, what actually creates that boost? And believe it or not, it's a nuclear explosion in your body. Okay? Certain nucleotides or radioactive elements are going to start decaying, okay, at a faster rate. And they will give you a higher radiation from the human body. If we move on to 8 o'clock, we get another boost. And then at about 10:30, we get another one. And then surprisingly, we get one at about 1 o'clock in the morning, or just before 1 o'clock in the morning, and about just before 2. Okay? And that's interesting, isn't it? Because we're asleep. Why would we want a boost of energy when we're asleep? Okay? Why would our nuclear reactors decide to start decaying and sending out a whole load of radiation? And I decided we'd try and measure what happens at these particular times. And it's quite interesting because they're associated with the various hormones in the body. As you'll see in a minute, the radiation is an expression, if you like, or generates the hormonal surges. And so each of these are periods of time. This is a period of time when the pineal secretes, as you'll see about. And then we have adrenaline ones, and then we have thyroids, and we have the thymus gland, and so on. So each of them is associated with a period of hormonal increase. Okay? But if you now superimpose the meridians on this, it gets really interesting. Because we work in our body clock, we work in 2-hour periods, don't we? We're all familiar with that. Are the new people familiar with the body clock and the 2-hour? That's great. Okay, so I'm not talking double Dutch. Okay. So the way I explain it to patients is that the body has a 24-hour clock, but it actually works with 12 meridians. So each meridian has a increased amount of energy, or its function, for a 2-hour period. And this is designed, or this is worked out with the level of the sun or the radiation from the lines of longitude. So at 10:30 in the morning, we are in 10:30, or this is what we call the now, or horary time as it's called. And this is a time period between 9 o'clock in the morning and 11 o'clock, okay? So it's nice and easy now because we've gone back into standard time, into winter time. In the summer, we advance our clock 1 hour artificially, okay? So in the summer, that period of time called spleen time, when the spleen meridian is most active, between 9 in the morning and 11 in the morning, will be 10 until 12, all right? So we just have to, you know, and patients think you're quite mad when you say it's 10:30, that's 9:30, and then you go in there and they think, oh yeah, he doesn't know what day of the week it is and so on. But we just explain that, you know, it's because of summer saving time, but the real time is actually the winter time. So we're very, very lucky here because we're pretty close to Greenwich. And Greenwich is exactly when the body clock will change and on each line of longitude. Now, being slightly west is irrelevant, you know, it's seconds really. When I used to live in Bath, which is, you know, perhaps 100 miles to the west, sometimes in the midsummer it was about 4 minutes after the hour when the body would change. So there was a time difference of 4 minutes there. Because the next time zone when the clocks actually change 1 hour is way out into the Atlantic, and the other end it's on the Russian, on the Polish-Belarus border. So it's a long way east. So in other words, to actually get the body changes. So a few hundred miles east or west of Greenwich is no problem. But when you're going to teach this in Berlin, it's very difficult because Berlin is 40 minutes ahead of here, actually, well, with the sun rising. And so their body clocks change at, you know, different times. So it's specifically, you know, 9 to 11. You've got to take these things into account. But we're very lucky because we can work on standard time and say, right, 9 to 11 is the spleen meridian is most active. Okay? And then 11 till 1 o'clock in the afternoon, it's heart and so on. And you're probably all familiar with these times. Okay? So what I've done is I've superimposed the 24-hour clock on this period. Okay, so now we begin to see we've got a boost at gallbladder time, we've got a boost at liver time, we've got a boost at heart time, okay, which is going to be about, as I say, 11:30 or so. And then we've got a boost at circulation sex time, which is what I always tell when this one comes out. I say it's nothing to do with sex. Okay, what it indicates is steroid hormones. Okay, circulation sex is all to do with steroid hormones, and steroid hormones are produced in the adrenal glands as well as the gonads. And then you don't feel bad about saying circulation sex. Okay? But don't confuse it with just saying circulation, because then that gets confused with the heart meridian and things. So then we get a boost on the triple warmer, which is bedtime, okay, which is an interesting one there. Okay, so that's, I want you to keep that at the back of your mind. So now we've learned that radiation varies summer to winter. It's normal for the body to give out a radiation. It's normal for a child to have a boost at the moment of the first breath, but this radiation varies through the day, through the 24 hours. So this would be exactly the same when it's 10:30 in Moscow and when it's 10:30 in New York, okay? So do you understand that? Okay, so it means that the now time, right now, when it's the same time in New York, not the time that it is now. Okay, because now is here at 10:30, right? New York is going to be, what, 5 o'clock in the morning or something. Okay, so when they get to 10:30, then their spleens will be the most active. All right, that's very important to remember. Okay, so this doesn't matter whether you measure this at 10:30 in Moscow, Vladivostok, London, or New York at the local time when it's 10:30. So you get these surges, and taking into account, remember the surges, taking into account the summer saving time. Okay, in the tropics you don't get summer saving time. In the southern hemisphere, of course, they're going now into their winter, so they're going into their summer, so they're going into summer saving time. So you've got to bear that in mind, okay, wherever you're teaching. So, okay. So these are some of the changes that Tatiana presented from the book. So we've got uranium, radon. They measured a lot of radium. They measured a lot of radioactive isotopes. And we contain all of these, and some of them will start buzzing at certain times of the day and then go quiet again. Isn't it amazing? And then a touch of uranium will come in the middle of the night, and then a bit of plutonium over here, and a bit of radium, and so on. And where it's got DAU, that means daughters, which are the offshoots of the radioactive decay of the mother substance. So radium will decay to a whole variety of other elements lower down in the periodic table. So DAU stands for daughters. So you've got thorium, uranium, radium, potassium, and that's the one we want to really look at. These are the ones they measured at different times of the day and the night. So during preclinical observations over average body temperature of the human body, the following results were obtained when they administered the magic compound, the stardust, on the rectal temperature. And they found that when they administered the stardust, the body temperature reduced by 0.1 to 0.2 degrees. This doesn't sound a very great deal, but it is a big drop in the body temperature. And when you drop the body temperature, you actually spare the production of free radical production in the mitochondria, because it's the speed of metabolism which creates the body temperature. Okay, so the higher your temperature, the more oxidative damage oxidative radicals you produce, therefore potentially the quicker you age. Okay? So dropping the body temperature down slightly actually creates longevity. Okay? It's a slower process, but on the other hand, you live longer because you don't decay so easily. The only way to reduce the body temperature range without damaging to the physiology is using an electromagnetic radiation. All stars do the same thing, all nuclear reactors do the same thing. Well, they have to be cooled. You hear about the cooling system. If you don't have that cooling system, you get a Chernobyl comes up. Stardust demonstrated the ability to maintain its ability to be a source of electromagnetic wave, which in turn is the reason for the temperature reduction. Now, when we come to learn what stardust is, we'll begin to see where these elements are in the body. So in ordinary life, a human switches on his own cooling system in the form of his own electromagnetic radiation 5 times a day, as we said. The fact of human radiation by energy of potassium. Now, potassium-40 is one of the most common elements which is measured as a radioactive substance. It's pretty universal. It's within us, it's within everything, so it's quite easy to measure. This is a powerful energy related to human cardiac muscle. We know that we use, I think it's something like 75% of the potassium that is used in the body is used in the heart. Okay, so the heart is the main place where we use potassium. Okay, so it's all related to the muscle contraction, isn't it? The regularity of the beats of the heart and the muscle contraction. So potassium is very, very important. It's hardly ever mentioned with a recommended daily allowance because it's almost very difficult to be deficient in potassium unless you're on diuretic medications or other medications. So they put an RDA of about 4 grams, which you tend to get if you eat enough fruit and veg. So to get potassium deficiency is relatively rare, although it can occur. Particularly I found with people with high blood pressure. So don't forget to test people with potassium. And particularly we find potassium chloride, potassium citrate is very good. If you don't test the people with the right type of potassium, sometimes you don't pick it up. You know, if you test with potassium sulfate and they don't strengthen to that, you might think, oh, well, they don't need potassium. But if you test them with a citrate or a chloride, then they might do. So just bear that in mind, particularly people with stubborn high blood pressures. So potassium is mostly used in the cardiac muscle. A heart, now it begins to become interesting. A heart, even segregated from the body, continues generating electrical pulses as a result, which the heart spontaneously contracts, provided that it is supplied with sufficient quantities of potassium and oxygen. We all know the chicken experiment back in the 1920s, when the chicken's heart was cut out, put in a medium with the right pH and things, and continued to beat apparently for 23 years, till someone changed the medium and the pH and the thing stopped. You know. So in other words, you could take your heart out, put it in a big dish with the right potassium and electrolytes and pH, etc., and it will continue to beat. Okay? So which is you? Are you the heart here, or are you the rest of the body and the brain over here? You know, but we do know it has an inherent rhythm, which has always fascinated me. Why does the heart have an inherent rhythm? You know, where does it come from? Nobody knows. You know, we've got cardiocytes, you know, specialized tissue in there, but still nobody actually knows what generates that electrical charge. The myocardium of an adult consumes 70% of the total potassium. That's what I said. Now, radiation by radioactive potassium-40 was absent both in the pregnant woman in their late gestational stage. So in other words, the woman was not showing radiation from potassium at this stage, and at the moment of delivery. So at the moment of delivery, nothing happens either. Okay, there's no radiation coming out, remember, any more than what is there to begin with. Okay, so the magic doesn't occur until they take their first breath. Then you get an increase in potassium-40 activity. It was measured only in the beginning of the postnatal supervision, between 2 to 10 minutes after delivery. In other words, that period of time when you wait and you wait and you wait, and the baby takes a deep breath in, cries, or then you should cut the cord, shouldn't you? Okay? You should not cut the cord before that period of time. So if you didn't know that, you've learnt something today, okay? Because the penalty is far greater than what we'd imagine. The heart of a fetus has an interatrial foramen. This is a patent ductus, or a hole in the heart, it's correctly called, between the two atrium. Okay? And because the fetus doesn't breathe oxygen, so it gets the oxygen from the mother through the umbilicus. So it doesn't need to circulate the oxygen to the pulmonary vessels, okay, through the lung. It just goes straight from the ventricles and between the atrium and the ventricles. So it doesn't generate oxygenated blood itself. It gets oxygenated blood coming in through the umbilicus. So, okay. So it has an interatrial foramen in the interatrial septum between the right and the left atriums, and blood can flow unrestricted between these two. After a child takes his first breath, the following happens. The interatrium foramen stops functioning and overgrows. Normal foramen size is 4.5 to 19 millimetres. Now, 19 millimetres is just under an inch. That's a fair size, isn't it? Fair size hole, potentially, it could be. I think there's a picture of one. Okay? So you can see this is an adult and the nail. So we're looking at something about the size of a thumbnail. That's pretty big. Okay? So, should the umbilical cord not be cut immediately upon delivery, in 5 to 10 minutes, the glossing, pulsing stops on the cord. Okay? So you've got this nice glossy, because it's full of blood, and it pulses. Okay? But when the baby takes its first breath, it doesn't need that anymore. Okay? So it stops, which certifies that the interatrial foramen has overgrown. And the heart has turned into a pumping system from the communicating vessel system. This is an unexplained phenomenon in the heart. So at this point, when you wait, and you wait and you wait, you wait for the cord to stop pulsing. Okay, so that means the baby is now producing heart contractions without a hole in the heart. Okay? So in 2 to 10 minutes, something the size of your thumbnail has overgrown. Okay? That takes energy. Okay? And where does that energy come from? It comes from the spurt of radiation. That's why the child has the spurt of radiation. That radiation would probably kill you normally. It's so big. But it's so healing and so fundamental. And it occurs at the moment that you take your first breath. And the reason for that, the whole mechanism, is to seal over the heart. It's now been discovered that with proper equipment, that possibly up to a third of the population have got patent ductuses. A third of the population. And that brings us back to the sort of seminars that we did during the summer related to phonocardiography and hypoxia particularly. These are possibly your people who you really can't get that oxygen level up because they've still got a patent ductus. They're transferring unoxygenated blood into the oxygenated cylinders, and you're on a losing wicket. Okay? And we don't know a way of doing this, but I reckon they had their cords cut too quickly. Okay? Now, you're never going to know when your cord was cut, but I know when I was not allowed into my first child because she was breech. And then the second child, I was allowed in. And I saw this thing coming out, this grey, hairy thing on the top. And I said, "What's that?" And the midwife said, "That's the head, sir." So after that, I learned to keep my mouth shut. But I became an expert as I had more children. But after that, the great moment was that the father was allowed to cut the cord. You know, this was really special. This was 1980s or whatever, okay, when the father was allowed to. So as soon as the baby comes out, and there's all this mess around the place, the midwife will hand you the child and say, "Would you like to cut the cord, sir?" And of course, I never thought, should I cut the cord? You know, I remember cutting the cord and that sort of gristly feeling with the scissors on now. No mention was made that the time is ready. Oh, look at the cord here. In more so-called primitive societies, they watch the cord, okay? And that makes a world of difference, okay? So it's a matter of when you cut that cord. If you cut that cord too soon, the chances are you don't get that surge of radiation to heal the heart. So the heart never actually, the patent ductus remains. So you may end up with a hole in the heart and never know it, except for the fact you're a little bit breathless, more than what you should be. You always show to hypoxia, and maybe you get other problems related to low oxygen levels in the brain and the muscle tissues, and maybe you never win any races in the athletics and things like that. So that's the reason for that. So it's quite a big hole there.